Hi everybody and welcome to our class. Our class is going to deal with respiratory flows and also drug delivery and inhalation. But before we're going to start, let's all take a big inhale through our lungs. How amazing is the lungs? The lungs just at that moment switch between carbon dioxide and oxygen, but also did something very, very unique. The lung block and filter particles not to enter the body, because if somebody is smoking, somebody make a fire, from evolutionary perspective, we don't want it in. But this also do for us a lot of problems. So let's talk about drug delivery and the lungs. So when you think about drug delivery, you probably think about injections, maybe through the digestive system, but how often do you thought about just inhale the medicine? And to understand that very truly, we really need to remember what is actually lungs, how it's look like from engineering perspective. So I see the lungs as a tree, upside down tree. You have the main stem, which split into branches and split down to the smallest unit of breathing, which is the leaf. And let's hope that the video would work. Oh, yes, it's working. So as you see, the lungs is the upside down tree. You have the trachea, which split to the two bronchus, which split to the bronchioli, which end up like the leaf in the smallest unit of breathing, the alveoli. And in the alveoli take place what we just talked about, the gas exchange between carbon dioxide and oxygen. And this region of the lung is very, very interesting, because you see this capillary, which have a wall of 1 micron approximately, so particles can penetrate this wall and get into the blood, and it's very, very unique. You have a lot of alveoli, a ridiculous number of alveoli inside the body, and the area of the alveoli with connection to the blood is approximately a tennis field. And if you want to consider how much blood interact with the lung, is actually a glass of wine that I would not resist at the moment, 150 milliliters. So let's talk again about drug delivery through the lungs. Everything sounds perfect, but there's a lot. So I want to talk about the advantage of the drug delivery through the lungs compared to the other ways. So if you consider treating the lungs, asthma, COPD, many diseases that are taking place in the lungs, the shortest way to go there is not from other direction, it's directly to the open door, which is the lung. Another very, very unique thing is that the medicine can reach in a very short time, because it's just the breathing time, few seconds. And when you consider systemic, to deliver through the alveoli into the blood system, you can think about Afrezza, a great company that do insulin using inhalers, and it's less degraded. It's not like pills that need to go through the liver, and it's highly dispersed from the lungs to the heart, everywhere, not like a syringe, which is very targeted to a specific location. So far, everything sounds perfect, right? But why we are taking this class? Where's the problem? We are engineers. We want to solve stuff. So let me share with you the main problem. So if you're gonna think about the alveoli as our target, and we compare all the different particles that can reach, we see that merely 50% of the medicine can reach the alveoli. And you see for every size, you have how much particle deposit in the body. The position, it's like in Hebrew, shikua. It's like sfiga, okay? It's how much being absorbed into the body. And if we want to check the terminal bronchioles, it's something like this, if I want to treat disease in the lungs, which mostly take place in this region. So you ask yourself, okay, where is most of the medicine? Most of the medicine ends up in the upper airway, head and throat. So that's what we have. So you think to yourself, no problem, Ron. Let's target this region with this specific size of aerosols and particles. However, you can reach these sizes only in a laboratory infrastructure. If you have off-the-shelf devices, you can reach only that one. So these peaks actually end up in these peaks. And for kids, this is even worse. And you want to know where is actually, what I show you right now is a healthy lung. Let's talk about a disease lung. What's happened when you have asthma or COPD, some inflammation in the airways? So they become inflamed, they increase in size, both radially, but also in the negative direction to the center. And that's what actually makes the diameter of the airway become much, much smaller, the effective diameter. And how this affects the lungs? Let's thought about it as an engineer. So if you think about the airway as a resistor and airflow inside our resistor, the resistance highly dependent on the diameter. And if from some reason a disease make it very, very small, the resistance would be huge. So no matter what are the chances of your medicine to deposit in a specific region, there's not going to be any flow inside this area. So there's no way to treat these places. So we really need to think outside the box. And this is very concerning because lung disease, especially COPD, is the third reason of death in the Western world. You cannot treat this location. So what's the goal of this class, especially the tutorial? We want to focus on these small guys, you know, that getting outside of the inhaler and understanding what's governed them, what's happened to these particles. So let's start by doing that. Let's try, you and me, figuring out what is the syllabus of the class, okay? I'm gonna go to that board, okay? So what is the syllabus of the class? What would affect particle deposition? Ideas, right, for particle deposition. So I want you to answer ideas, mechanism, forces, stuff that you think that would help us to control the particles. What do you have in mind? What? Viscosity. There's air inside the lung, so the particle most probably being inside this region of air, right? So there's going to be a drag force because of viscosity. So we would like to know how the particle move inside the airway, which is our second, very good one. Another option? What force right now make me stand and not gravity? Perfect. So if I want to deposit a particle, gravity can help us, right? So gravitational, right? Huh? Somebody know my PhD? Yes, my PhD is about electrostatics effect. So indeed, if a particle get with a lot of friction from an inhalers, it's going to be positive or negative. And when it gets close to the conductive tissue, it's going to polarize it. And yes, we're going to have an attraction. Very good. So electrostatic also can play a role. What else we have in lungs?
Pressure gradient.
Huh? Pressure gradient is come to that. It's a really good point, yes. Huh? Diffusion, definitely. The air around us is not a vacuum, right? So if we're coming back to this point, so we have some nitrogen, right? Some CO2, some oxygen, and they want to hit our particles, right? And so we're going to have some effect of diffusion, definitely. So, and this will take place in the region with very low velocity, the acina region, the alveoli. Yes, this is the place. What else? Be creative, guys. In the lungs, we have relative humidity, right? Relative humidity of 100%. So particle can increase in their size because there's going to be some water around them, right? This is the original size that you have. And suddenly, water just jump into it, right? So I do this small Mickey Mouse is H2. Or maybe the other way around, what would like to run away. So the diameter can control by time inside the lungs. It's going to be in certain size in this location, but in that size and that location, it can change its heaviness if you're thinking about it, right? So what else? Temperature. Temperature, yes, it's coming to here, to diffusion. This random motion of these molecules is due to temperature. Very good point. We can be very fancy and exotic and also talk about external forces, maybe magnetic, that's gonna trigger the particle to come to some direction from outside. We're doing that in our lab. And we also can talk about one of the basic things. Think about cars, okay? If you have a car with a very high velocity, it's not easy to take sharp turns, right? That's what happened here, you see? This 90 degrees it's very hard. This is called impaction. Impaction. So it's hard for the particle to take this 90 degrees angles, and it's going to hit the wall, and sometimes also just a normal split. It's very hard to take it. Oh, I did not succeed to turn in time. The flow or my size was not that adjustable to it. Also, we can think about that particle can be stuck. Let's talk about the interception. If we go breathe asbestos, you have a shape, a very unique shape. Let's come to the drag force. Very unique shape that it can penetrate very, very deep, and suddenly it's going to be stuck inside because it's very, very big. So stuff can just stuck inside the lungs. Okay, very good. I think we covered most of the stuff that we want to talk. So each one of them in a perfect semester, I think we're going to touch all of them. It really depends on our time and what's going to happen. But today I want to talk about gravity. Okay? Perfect. And what I want to do, let's go to the slides. So back to the slide. So if you consider the lungs, I want you to see something very, very scary about the lungs. The lungs is a multi-scale problem. What do I mean by that? This is a few centimeters, and the alveoli, it's in the micrometer size. You need to run your equation on very, very different scales, okay? So this is a very problem. So if you want to consider gravity effect, so sometimes it's going to be very strong, and sometimes it's going to be very weak. It really depends where are you inside the lungs. And we know that gravity plays a significant role on particles because we check that. You see, this is a parabolic flight. They're doing this thing, and they can increase or decrease gravity. So that's what people did in NASA. Okay, they give to many people to inhale during flight, and if you want to look at from the side, you see there's no gravity in some places, and gravity significantly change the amount of the position we can have inside our lungs. So this is a very concerning how we can treat people out of space in Mars to help Elon Musk, right? What you're going to do without gravity, right? So that's what we're going to try to do to help Elon Musk. And I want to remind you, as we talked before, so the dimension of the lungs changing dramatically. So we have change, I'm going to here. So we have dramatic change in the diameter of the lungs. Do we have here another blue? Take this one. So we have a dramatic change of diameter inside the lungs. It's changing and become very, very small. And also the velocity always change because the flow rate change as well. If I have here 100 liters per second from my inhaler, suddenly I have only 50 in each lung, right? And then again it's going to split and split. So we have this phenomena that our initial Q is always decreasing, right? Z is like the generation inside the lung, okay? So you don't need to write it, just to understand that we're dealing with the multi-scale problem. How can we deal with the multi-scale problem very efficiently? Do you remember for fluid mechanics how we did it? Scaling. And if we want to understand what's governed the equation and want to do it properly, we need to do Buchanan-Pi theory, right? So what I want to do next is recap Buchanan-Pi theory, and then I want to solve the same equation. I want to solve the falling ball equation. So we have here a ball, right, with the mass m, some initial height, yes, gravity, and I want to solve it in a few ways. I want to solve it with Buchanan-Pi theory, okay, to do a reminder. Also good for the people for the exam in fluid mechanics, right? And also I want to do it with Newton's second law because we know this is an easy equation, right? But if we're going to solve them both and compare them, it's going to help us to understand how we can use non-dimensional I and when it's come handy, even though when we don't know how to solve the equation. In our case, we would know how to solve it, right? So let's clean here. So let's do a reminder about Buchanan-Pi theory. Buchanan-Pi theory, going back to the board, is talking about this concept. if you want to do an experiment and you know your governed parameters, for example, let's discuss what's the governed parameter of this situation. Some initial velocity v0, right? Falling ball. What's initiated the process? Gravity and mass. Initial height. And what want to stop gravity? Yes, definitely drag force. Drag force. So we have here something that plays with drag. So I want you to see that the drag force, the parameter that relate to drag are going to symbol with K. Okay? What is K? In our situation, K is if you have the force, the drag force, is proportionally to the velocity, right? So I'm going to put K, and the reason I'm choosing this force and this K, because I want to connect it later to Newton's second law. So we're going to choose K, and what this K actually presents to us is kind of the idea of a lamp model. It presents the viscosity of the surrounding, the shape, and even the velocity we are dealing with, the regime of velocity, right? Like all these parameters actually more complicated than they really are, right? G we can think about M. And we can think about the density and the particle diameter, right? G, it's the mass of Earth, the radius of Earth, right? The constant of gravitation. So this is, remember, this is our some lamp parameters gonna present a problem. So instead and going back to the presentation, instead of doing experiments on each one of them, gravitational, velocity, K, the mass, it's gonna take a lot of time, right? Think about 10 experiments each, 10 to the 4. If experiments 30 minutes, you're working for 1 year, 8 hours a day, that's going to take 2.5 years. It's a lot. So what is the best way to do it? The idea is Buckingham pi theory to understand what is the simplest parameters I can use to solve this problem. So how are we going to do it? I'm going to present you the method. So pi theorem, and we're going to start from the end. So this is the steps. Here they are. Here they are is who are the physics parameters we need to know to actually solve this problem, right? The general one. So we just write them on the board. So right now we're doing H. So I'm going to put them in a table. So we have the mass, we have the velocity, we have the gravity, we have the initial height, and we have K. Right? So, and what we're actually doing is taking care of the units. This is our parameters. And in our case, how many do we have? We have n equal 5. So this is the first step. The second step of the method is to realize what are the units of these parameters, because we want to simple it down. So what are all the units that we have in physics? It's narrowed down to only 5. What are they? 1, 2, 3, 4, 5. So what are the basic units? Mass, perfect. So we have mass, we have length, we have time, and we have 2 more. We have charge, can be, and we have temperature. T is taken, so we're going to do this thing. Okay? So most of the time, we're going to use only MLT, mass, length, and time. This is more exotic, but it doesn't need to stop you if they do appear, right? So we want to present the unit of each one as a power. Okay? So how many mass we have in normal mass? Only 1, and 0 of that, and 0 of that. Velocity is 1 meter per 1 second. It's per, so it's a negative. Gravity is 1 meter, 2, right? H is easy, it's 1. What is the unit of K? If you don't remember, you can go here, right? This is Newton. Newton is kilogram meter square, right? Meter to the second square. And here we have, this is what we want to find. Velocity is meter per second, meter, second. So we end up with kilogram per second. So it's 1 and minus here. Here, So far, it's okay? Perfect.
What is the...
Yes.
Keep the I?
What?
What is the...
This, it's actually capital theta, okay? And it's for temperature. If you learn heat transfer, usually use that one because this is over most of the time taken by time. Okay? Perfect. Good. Definitely. Great question. She asked me in the audience, how did I know that K is not to velocity or velocity squared? So most of the problems in the lungs gonna deal with a linear term, which is gonna be easy, but in the homework, you're actually gonna get here squared. So be careful, so the units of K gonna change, okay? So we can put here K1, not to get confused, but you're definitely right. And if you want to know something interesting, sometimes you have both of them. You have also KV and also KV squared. You have two parameters, okay? So, but this is the question that we have, a more easy question. Great. The next phase of taking Amphitheory is to do a distinguish between our independence and dependence. What do I mean? So you see that I did not need this one, right? You saw it? I don't need them, which means I have in my problem R equal to 3. I just need 3 units, okay? And I need to decide who's gonna be my units. I need to choose independent. So I'm just gonna do this. And I'm gonna say this one will take care of the mass. This one can take care of the length dimension. And this can take care of the time. Okay, great. So right now, we have this one as our independence, right? Independence, that's gonna be our dependence parameters, right? So how many do we have here? We have n equal to, we started with 5, minus, we have 3 independent, so we actually have 2 pi parameters, okay? What do I mean by pi parameters? Pi parameters is actually very, let's write it on that side. The eraser, here it is. Okay, so all that we did at the moment was trying to figure out how many pi's parameters we have in our problem, and that's tell me how much can I shrink the problem to simpler one. So I'm just gonna press and come back there. Here it is. Okay. So we have 2 different pi's that we want to find. Pi 1 and pi 2. And these 2 parameters can actually describe all the story of a falling ball, even if I don't have a theory at all how to solve it. I don't have any equation. That's the force, that's the power of this method. So how do they look like? So I take the one that left. I have, for example, H0, and the thing with the pi parameters, they're actually unitless, okay? So I'm gonna put down below my dependence parameter, M, V, G, and I don't know the unit that they have, A, B, C, and the last step of solving it, let's do here, pi 2. The last step of solving it is to realize what is ABC, and then we're gonna find A. And to do that, I'm gonna make the powers equal. What do I mean by that? What is the unit of that term? M is to the power of 0, V is to the power of 0, to the power of 0. Okay? So here on the other side, I see here, actually I can present. We see here length, sorry, let's write that even better. We have units of length, mass to the power of 0, unit of length to the power of 0, and unit of time to the power of 0. And on the other side, I see h as length, right? Mass to the power of a, velocity to the power of length over time, b, and gravity L to t squared. C, right? I'm gonna change it to black pen. תביא, נשמח. Okay? And we're gonna solve this equation because I see here actually 3 equations. I see equation of the mass, of the length, and of the time. So the first equation of the mass is 0 equal to no mass here, 0. But I see below a mass in power. See it? So the powers tell me that A equal to 0. Perfect. Let's do the length one. This is 0, right? Here I have 1 thing minus B, right? I look here, minus C. So I see here that B plus C equal 1. Nice. The last one, the time, 0 equal 0 minus, because down, I see the T is in the denominator, so I get another minus, right? Here I got minus C, right? C, but I'm in the denominator, another minus, and I see this 2, right? So from here I can get that C equal minus 1, and then from here and here, I can get that B is equal to 2. So we right now can write pi 1 as what? Let's do it here. Pi 1, can I take it up? It's gonna be easier for me. Here it is. Okay. So pi 1 equal to what? To h0 divided by m to the power of 0, v to the power of 2, g to the power of 1, and we can write it nicely packed as this. This is unitless, and I don't have a clue what this is present. But I want you to look at something. Let's just add mass to each term. What do I have here? Do you recognize what the top thing is? Huh? Yes, it's potential energy. And down below it's kind of a kinetic energy, right? So I don't have a theory. I don't have a clue what's going on in the problem. But Becky and pi theory tell me, Ron, just know that this ratio is important. And because Newton said, no, actually not Newton, Leibniz talk about energy. So just said this ratio is important, even if you don't know what it is and you don't have a theory. So apparently, the potential energy that I have and the kinetic energy is very important to solve the falling ball problem. And we know that. And we suddenly have some intuition to it. So it's crazy, but this recipe how to make a pie cake, right? It's actually telling us something that's familiar to us. And this is a very famous pi number. Actually, it's called the Froude number. And write the opposite way around. E-kinetic, it's actually not energy, you know. It's unitless. You see, before it was not energy. It's actually the idea of gravitation, sorry, below. Gravity versus inertia. Inertia, which means I have a lot of force, a lot of velocity in one direction. So you can present it as energy, but the real concept is that. And Froude was the first one to actually design a very, very good ships. How he did it? He take into account this height of the wave and the velocity that the wave hits. The velocity that the wave hits the boat. And using this ratio, he built a very good ships. And this is the first one to realize this ratio is important. So this is the Froude number. In the same method, it's a really tedious process, right? It's just math. It's okay that I'm going to give you the result of the second one? Yes? Okay. So everybody remember fluid mechanics. It's great. So pi 2, in our case, it's going to look like this. It's going to look like K V0 divided by mg. Is this familiar to you? What is this ratio means? Definitely. So here below, I see gravity effect, right? the thing that right, it's actually balance of forces, you see it? What is Newton's second law tell us? That if we're going to solve it by Newton, it's going to be sigma Fy, right? May, right? We have two forces, which are gravity, right? And the drag. True. And we can present it even nicely. Gravity if I'm going to do y-axis at that direction, the ball is falling. The ball is falling at that direction, right? Gravity. So we have minus mg and a drag force, which is k multiplied by v. What is the sign of here? So all the people that said plus, I make you, I on purpose did that. I want to fail you. The reason is that here there's a minus. Somebody in the audience remember why we should have here a minus? Exactly. The velocity tell you what the sign should be like, right? If the velocity is negative, so it's minus the velocity. It's do the opposite way. So the drag gonna be positive. Don't forget it. Okay? Yes? So always be careful. It's even easier than you think. It's always minus. I don't know the sign. It's always minus. I don't need to care about it. But be careful. Where you should take care of the sign, when you do the v squared, you lose the sign in the homework, right? So here you do need to put the sign, okay? And if you're gonna write it as a MATLAB code or simulation, you should do minus kv multiplied by absolute value of v, right? And then you are okay with the sign. Okay, so just remember these two, okay? kv, absolute value, or kv, and you need to determine if it's plus or negative. Okay, this is the two ways. Great, and here we can write m d v dt, right? So what we see here is actually a balance between these forces. So gravity wants to pull the particle down, but drag force wants to resist it, right? But drag force enjoy the acceleration, right? So I want you to see something that it's not about forces, right? Gravity, friction, let's say, right? Drag, something that tries to stop me. It's the balance between them. So I can present it differently. Look, if I'm going to present it like this, somebody know what is this velocity? Exactly, this is the terminal velocity. This is the final velocity of the particles. Let's go here. If you're going to look careful at that equation, I can reorganize it and write it that way. I can write it as dv dt plus v plus v equal minus g, right? And here I can put k over m. And you see that this ratio actually have a time unit. You see it? It's the characteristic time of the particles. So this is actually dv dt. We can write here tau, 1 over tau, tau v equal minus g, right? And if we're going to solve it to the steady state solution, what's going to be the velocity in the end? We're going to see that v equal g tau, which is minus g tau, which is exactly this one. If this is tau, right? Tau g is the terminal velocity of the particle. We saw that in physics 1. We saw it in fluid mechanics. Okay, great. So what we actually had, we got this pi 1 and pi 2. You see it? So they are very, very important. And I know that we can solve this equation, right? So I'm going to go to that side of the board. So in our case, we have been lucky, right? Because, let's clean that. So we do know how to solve Newton's equation, second law. It's an easy derivative ODE question, right? It's just that. I can present that v is actually dy to dt, right? Can present it that way. And then my equation is actually dy square dt square here, right? Derivative twice, plus 1 over, I can do it, yes, 1 over tau g, which is the terminal velocity, dy to dt. Actually, let's not use tau. Let's use k over m. I just got to write the equation.
For what?
This one, Newton's. I just write, this is Newton equation. We started from here. This is just a side note. We just apply for the distance, right? V equal to dy to dt. I put it inside, equal -1, right? This is the equation that we have about falling ball. Physics 1, right? Physics 1, what is the initial condition that we have? We have that in t equals 0, the ball is at the height h naught, and we know that the velocity of the ball initially was minus v naught, right? This is the equation, and we have a solution to that equation. We're not going to waste time on it, so the solution is very messy. Vt equal to tau g minus v naught exponent tau minus tau g, and y, how we call it, tau minus exponent tau. I want you to see how awful this equation is, okay? Because that's the reason I want the non-dimensional. So this is always hold. You see this down below? This is the solution anytime, okay? Anytime, any condition. But in the lungs, when we solve a multi-scale problem, we don't want this solution all the time. Sometimes stuff of the equation are negligible. And today we were lucky. Today there was a solution. Navier-Stokes, Maxwell equation, the force on a particle, not always going to be that solvable, okay? So we need a method how to skip on this phase and find the result that actually interests us, okay? How are we going to do it? So I'm going to use this concept of non-dimensionals. So I'm going to clean here. Okay? And let's scale the problem, like we did in Navier-Stokes in physics, in fluid mechanics. So I want to present a new parameter for y and a new parameter for t, okay, which gonna build off some characteristic length and just something approximately 1, which gonna present just the time and the height. So what's gonna be a fair choose for y? What is the characteristic heights that we have in the problem? H, like the only given data that we have. What we can put here? We actually have two options. You can try them. We can put tau, but I want to talk to this guy. How can I talk to this guy?
H over v.
Definitely. I know the distance over velocity give me time. So I'm going to use that one, but you can definitely try it. And I think in the homework you're going to see something similar for choosing this case. Okay? Perfect. Also, I want you to see that our equation definitely changed. Look what's happened. If you're going to take dt, right? And right now, instead of u, we're going to put u tag, right? What's going to happen? So instead of u, I need to put u tag and hfs, h node.
You mean y?
Y, sorry, yeah. Y, exactly. Y tag. I switch this one with the non-dimensional that I have, right? H node. And for t, I'm going to put this one, right? So h node v0, and it must be square, you see, because you have your square, plus, I see there k, right? mg, and there what I have h node dy tag divided by dt. dt, it's easy. It's minus, it's that. Done. V0, right? True? And now it's equal to -1, of course, right? That's what we have. And now we're going to simplify the equation. What do we have here? If you're going to write it organizedly. So this cancel with one of them, and this is canceled. So we end up with V0 squared, H0G, D tag, D tag, DT tag, plus KV, MG, right? dy tag, dt tag equal -1. Do you see something familiar to you? What? This one? This? Sorry. I divided this equation by g, so here should be a g, right? So g, right? Thanks. Very good catch. So what do you see when we did this normalization to the equation? This is unitless, right? What's the unit of 1? Unitless. Unitless, unitless. And then if you look very carefully at this term, and at this term, and at this term, what we actually have here is our non-dimensional parameters, okay? So now it's like the big thing of the tutorial is, I'm gonna give this one a name. I'm gonna call it CD, okay? CD, it's not the official name of it. I usually call it H to the -1, but we're gonna discuss it later. Today, because it presents friction, let's call it CD, okay? So we actually end up, we're gonna clean that one, we end up to an equation, very, very interesting. Turn down the, turn down the projector, yeah. So what we actually got is this thing. Yes, I'm going to turn this on. Yeah. So we actually got that our equation look like this, right? We have fluid in the front, right? Square, square. We have CD, dy square, dt square equal -1. And I want you to see something very interesting. If we're gonna consider a case when CD is very strong, CD, one of them, you see, together they are building the -1, right? But let's say that fluid is very small. Fluid number is very, very small, which means this term is actually what? Approximate to 1. So what actually happened? We have this equation to solve, right? This equation. And we can also return to the normal equation. We know to replace the non-dimensionals. And we're going to get that Vt equal to minus tau g. And the height in time is that. It's just a linear. You see it? What happened? The friction, this is small, this is big. The friction, this term, is so strong that you don't have conservation of energy. Immediately the friction takes you to a terminal velocity. You don't need to solve the hard equation. You need to solve that equation, which is easy, right? The first derivative divided by CD, right? And in the other case, let's say that CD is very, very small, which means you don't have friction. Fluid is approximately, with the derivative, this one, so you have dy squared, dt squared, right? Equal to -1 over fluid. Solve the equation, right? And you're going to get to yt, h naught. You're going to get to trajectory ball falling from physics 1. That's what you're going to end up with. So what I want you to see is that in the extreme, this is the solution, okay? A lot of friction, non-friction, only conservation of energy. You see it? And I'm going to show you the results on the board, on the projector. So for example, if we consider the first one, look, I changed CD. I change it. I can change many parameters. I can change the mass. It doesn't matter. What matters is what is CD. It's going to tell you how the map look like, okay? And here I present the non-dimensional y, which means y divided by h0. That's the reason they all start at 1. You see it? And also the time, I normalize it also. It's not tau. It's a t tag in our way of writing. So you see the different path. If you have a lot of friction, it takes a lot of time for the particle to fall. You see a lot of CD playing a role. And for the other one, if you consider this case, you see, actually this is not a good figure, but I want you to see the trajectory that we have, the parabolic falling, okay? So what was the point of this tutorial and what you're going to see at the homework? So if I'm going to think about it, the particle dynamics going to be messy. They're going to be electrostatic force, which is non-linear. They're going to be drag, sometimes drag to the square, and many other problems. And it's not related really to the lungs. You can use the same equation and solve a problem about drug delivery in the blood. It's the same force, the same equation. CD would change. Food would change. This one. But the game would stay the same. Say, for this food and for this coefficient, the drug coefficient that we got, I know that I need the right equation, not the left one, okay? And the equation, you know, you are almost engineers, guys. You're going to finish. And the problem that's still facing challenge today are the problems that don't have a solution. That's the reason you are here and people pay you money to do it, right? So the idea of this method is to help you distinguish, do I really need this ugly solution? Maybe it's not exist a solution. Navier-Stokes, we still don't have a solution. But we know that using Reynolds, using Struel, using food, also this one appears in Navier-Stokes, we can simplify Navier-Stokes to something that we can solve. The same thing would happen to the particle dynamic. And you can use that. The idea of the class is that you're going to end the class, use these ideas, and solve drug delivery in the lungs, in the blood, or even if you have a microchannel and you want to sorting your cells. Okay, the cell is a particle. I want it to go to the right and not to the left. You can do that with that equations. Okay? So the idea of the first homework that you're going to get is just to play and repeat what I did. Maybe not in a 1 hour, but you have more time at home, so you can do the v squared. You can solve the ODE, how you're supposed to solve them, the Madar ODE, right? And do everything. And each homework, I'm going to give you a small MATLAB, just to see that you realize and increasing your understanding. And it's going to build up to the final project, okay? So hope you enjoy this class about just reminders what is fluid mechanics and how to deal with drug and particles. And I'm going to see you next week, unless you have any question right now. Okay.